Tree diagrams are yet another method by which we can represent data to help us visualize in order to answer a question. In this case, the kind of data scenarios that we'll probably be working with are ones where an event happens, there's a probability of either one outcome or another, and then after that has happened, a second event also happens, either something completely separate or the same thing again, either with the same probabilities the second time around or something different. To best explain these, it's probably best to just go through a scenario off the bat. So, 20 pink and 18 yellow counters are mixed in a bag. 2 are selected without replacement. Draw this tree diagram. So, already just reading through here, we have an option. It's the counter that's going to be picked is either going to be pink or yellow each time that one is picked. This is only 2 options, so from our starting point, we have these branches, one coming up for the pink, one coming down for the yellow. Now we're going to want to identify what the probabilities are in each case. Because it's a probability, we'll say how many fit each criteria out of the total. For the pink, there are 20 pink to start off with, out of a total, if we add them together, of 38. And similarly for the yellow, that's then 18 out of 38. Now in each case, regardless of whether you took a pink or a yellow the first time, when it comes to picking the second counter, because 2 are selected, you are presented with that same choice of either getting a pink or a yellow. And we're going to have these branching off from each of your previous endings respectively. Regardless, in this case, the probabilities are going to be different depending on what you took first of all anyway, and we'll get to that in a second. But regardless, even if these probabilities were going to be the same as the first time round, let's say that we had replaced the first counter before picking the second, still you have to think of it like each root is going to be taking its own path on the tree, right? Your roots aren't going to keep intersecting with each other. This yellow here, even though technically it's the same as taking a yellow here, because they're both your second counter is yellow, this taking a yellow the second time is specifically after taking a pink the first time, whereas this is taking a yellow the first time. They're different timelines or different paths of possibilities, permutations, if you like. So they're always going to be spreading further and further apart in their own separate branches, regardless of if they are technically the same event. Now, on that note of the probabilities changing because this is without replacement, let's say that we did take a pink counter the first time. There were originally 20, but now that you've taken one away and you haven't put it back, there's only 19 left. So the probability of taking a pink the second time, well, there's only 19 to pick from. And the total, again, has gone down by 1. This will go down to 37. Now, meanwhile, again, if you're taking a yellow the second time, having taken a pink the first time, that total is still going to have gone down to 37, but the total for the yellows is still this 18. Whether you want to think of it as these two have to add together to make 1, because all probabilities in a given scenario have to, each pair, each V of branches always have to add up to 1. So if we know this is definitely 19 out of 37, this has to be 18 out of 37 to make it 1. Or think of it like how you've only taken a pink so far, so there's still the same number of yellows left over. There's still 18. The total always goes down by 1 if it's without replacement, but the numerator only changes if it's the same as the one that was taken previously. With that in mind, if you took a yellow first, now this pink here is still going to be out of 20 because you haven't touched the pink total yet. Again, it's going to be out of 37 though. And then took a yellow first to take a yellow second. If there were 18 but you've taken one away, there's now only 17 left. Again, out of 37. This is what your tree diagram would look like in this case. Now that we have this, we can look at the second part of the question, which would be find the probability that exactly one of these counters is pink. Now there's technically a couple of paths that we can take that would give us this answer. To go on both upward paths, as it were, that would be a double pink. That's not exactly one of the counters being pink, so we're not going to take that one. However, to get a pink and then a yellow, yes, that would be that exactly one out of the 2 counters that was taken was pink. Similarly though, if you were to take a yellow first and then take a pink, that would also be taking only 1 pink. And obviously yellow is no pinks at all, so not going to count that one either. Even though these both basically lead to the same results, the same outcome, that you'd have one pink and one yellow, you have to consider them individually. Any different path through the branches has to be given its own fair consideration. You have to count them all, and then you combine them at the end. When you're going left to right, when you're going along the branches, you times together any fractions that you go through. So in this case, to get from our starting point down to this y here, we'll need to go through 20 over 38, and then you'll times by the 18 over 37. Whereas for this other route, again, you're now restarting back to the beginning. We'll now go down the 18 over 38, and you'll times that by, we'll go up here, the 20 over 37. In this case, this is going to get you the exact same fraction at the end. Both of these are going to lead to 180 over 703 because it's the same numerators times in together and the same denominators times in together. It's just the numerators in the reverse order. It's not always this case. Sometimes these fractions in the second time will be drastically different to the first time round, or it depends on, which permutations of fractions of which letters you're going to be going through. So it is always advisable to go through each of the possibilities and times together individually anyway, just to be sure. However, in a case like this, if you can spot that this, in this case there was only 2 versions, but maybe there'd be in another question 3 routes that would lead to the same fraction, or 4 routes, or so forth. If you can spot that they're all going to lead to the exact same thing because they are the same combinations of numerators and denominators, you could just work it out once and then times it by however many there are. Either way though, again, the fact that these are the same fraction at the end, that doesn't mean that this is our answer. We still need to combine these 2 roots. Now, if we've times along the branches, you'll now add down the solutions. So if you have multiple solutions, multiple paths fit the criteria, add together what this has gotten you at the end, and that therefore is going to give us 360 over the 703 for our answer for the probability in this case that exactly one of the counters would be pink. Well, those then are pretty much the fundamentals of your tree diagrams. It's just a matter of working, okay, how many branches are we going to have each time? What are the probabilities on each branch going to be to make sure they add up to 1? How do they change with each tier? All of this really just coming from the scenario. And then also just remembering that we need to times along the branches and add together any multiple answers we might get. You aren't always going to, but if you did. The complexity and difficulty of these questions then more just comes from the wording of the question itself. So with that in mind, let's look at the example on the right. So in a game, the probability of winning the first round is 0.2, the second is 0.5, and winning exactly 2 out of 3 rounds is 0.26. The 3 rounds are independent of each other. Complete the tree diagram. Now, in this case, we have 3 rounds, 3 tiers, 3 levels to the tree, 3 decisions that have to be made in each case, as opposed to 2 from last time. Another difference to last time is we don't actually have all of the information off the bat. We know what the probabilities are for winning the first round and the second round, but we're not explicitly told what's the probability of winning the third round. Instead, we're given something slightly different, that you'd win exactly 2 out of the 3. Now, when it comes to completing the tree diagram, therefore, if it's more of a 2-mark question or something like that, which it likely would be in this case, they are expecting you at this stage to work out the missing information. That will more come in the second part of the question. Instead, when you draw that tree diagram, you would just use some kind of notation to represent the missing pieces of information. Make of that what you will, and we go through in a second. Obviously, we'll see what I might use in that case. Neither way, just an acknowledgement that the fact that the 3 rounds are independent is telling you that in the third round, the likelihood of winning is going to be the same in every single instance, like with the other 2. It doesn't matter whether you win or lose the second round in terms of how likely you are to win the third round. It'll be the same each time, so you can use that same notation in each single case. Now, that being said, you can work it out now if you so want. You're going to need to eventually. I'm just saying it's up to you. So with that in mind, I'd just like you to pause the video and have a go at drawing this tree for yourself. Make sure you have enough room when whatever space you're doing it in, because you're also going to have to fit in all of the numbers and probabilities as you do it. So either just fill it out, draw it out as you think it's going to look with some notation to represent the missing information, or indeed have a go if you want at trying to find that missing information. Either way, just have a go for yourself and press play again when you're ready to compare. Okay, so to start off with, we'll just get the frame of your tree. On the left, we're going to have an origin, some starting points from which your first two branches are going to come, one for a win and one for a loss in that first round. Then regardless of how you do in that first round, we're then going to have two more branches for the second round, again coming off from each. And then the same is going to happen with the third, coming off of each of them like this. And again, try to give yourself as much room as possible. I've tried the best here, and you can kind of judge your space on your page as best as possible. Again, for each of these, just to make it clear which is going to be which, so have a win and a loss on each pair, and then we can go about adding on the probabilities. For the first match, if the probability of winning is 0.2, and in each pair the probabilities need to add up to 1, that means the probability of a loss is 0.8. Then in the second rounds, the probability of winning is 0.5, which makes the loss also 0.5. There's a half and half chance of each. And this will be true for both versions of the second round because it's independent. Doesn't matter if you won or lost the first round. Now at this stage, when I was talking about notation before, we could just say like maybe the probability of winning the third round is just P, in which case losing that round would be 1 minus P, because again they have to add up to 1. So far we've been focusing on the probabilities of winning, so that's probably going to be the one we make a notation for the probability of, leaving the loss then just being the counterpart. But again, you could really use whatever symbols you wanted, although I maybe would suggest making the loss 1 minus whatever you did for the win. And again, because they're independent, this is going to be all right for all of these third rounds. Now, in terms of working out what this probability is, if you did this at this stage, what we'll say is that if the probability of winning exactly 2 out of the 3 rounds is 0.26, well, which routes would be winning exactly 2 out of the 3? Well, that would be this route here, that would be this route here, or it would be this route here. These are the only 3 out of these 8 that have exactly 2 wins, and therefore by contrast 1 loss. So if we were to add up these 3 overall probabilities, it should get us 0.26. What does this look like? Well, timesing down the branches, we'll have 0.2 times 0.5, well that's going to be 0.1, and then 0.1 times 1 minus p, well that's just going to be 0.1 minus 0.1p, and we'll add onto that our 0.2 times 0.5 again, which again is just going to be 0.1, times now just by p, so it's now plus 0.1p, plus down here 0.8 times 0.5, which is going to be 0.4, and then times that by p, so plus 0.4p. Altogether, this is going to get us 0.1 plus 0.4p, because the minus 0.1p plus 0.1p are going to cancel with each other, and again we know that this equals overall 0.26. So to get the p on its own, we'll take this 0.26 and we'll minus the 0.1 from it, and then we'll divide by this 0.4 here. And that in turn actually gets us another 0.4 for our probability of winning the third round, which then by contrast means the probability of losing is 0.6. This is how we can essentially reverse engineer a probability if we need it. We can work backwards from an ending to get an earlier part if we can write out what the whole expression that gets us to that answer would be and solve algebraically. Either way though, just at the bottom here, now find the probability that 2 consecutive games are lost. Well, which of these paths would then have 2 consecutive games being lost? Now it would either be this branch here, so we have a win, loss and loss, a loss, loss, win, or a loss, loss, loss. Because the question didn't say exactly 2 games or just 2 consecutive games. Losing 3 games in a row, that's still losing 2 consecutively. So again, we have 3 outcomes that are going to fit this criteria. To work out the overall probability then, we'll just have to work out each individual version, then add them up afterwards. So for the first one we said, that's going to be your 0.2 times by your 0.5 times by, and we said that 1 minus p was going to be 0.6. Then down here, we're going to have our 0.8 times by our 0.5 times by our 0.4, and then lastly the very bottom branches 0.8 times 0.5 times by 0.6. Now in each case this is going to get us 0.06, 0.16 and 0.24. Finally, adding these 3 up, that's going to get you an overall probability of 0.46. Okay. Now, if you've seen enough of these videos by now, you'll probably know the format. We're about to go on to a couple more questions down on the next screen. For instance, the first one we're going to see, whereas this question here had 3 levels to it, tiers, whatever you want to call them, this next one, instead we're going to have 3 possible outcomes to each event rather than sticking with the binary that we have had so far. So here we have 17 cards are shuffled. 9 have the letter A written on them, 1 has the letter B written on it, and the rest have the letter C written on them. Ryan takes a card, notes the letter and puts it back. Then he takes another. Draw this tree diagram. So in this case, once again, we're in a situation where we want to be very conscious of space. What I'm going to do for the sake of fitting in here is my tree is going to end up looking a little bit weird, basically. My branches are going to be different lengths, but that's again just to make use of the space in this case. Because from our starting point, we're going to need to have our initial 3 branches, and we can see I'm already making one slightly longer, so that when I get onto these next ones here, I'm not fighting as much for space with this middle one here. Of course, ideally in the actual exam paper you would have a lot more space than this. You would have space to fully spread it out and try to make them even, but that's in nowhere criteria that they're going to be marking you against. Either way though, in this case, what we're now going to be labelling each of these branches are A, B and C, because those are the different options that we can get from each card selection. Now in these cases though, unlike with the above example on the left hand side where it wasn't replaced, in this case the card is put back before the second one is taken. That means that the probabilities in the first selection and the second selection are actually going to be identical to each other. The total is not going to go down. So here we know there's 17 in total, 9 have A. So every time we have an A appearing on any of these branches, we are going to label it as 9 out of 17. As for the B's, there was only 1 with a B on it, so every B is going to be labelled 1 out of the 17. And then finally, all we're told is that the rest have C. Well, we know there's 17 in total, and we've used up 9 that have A, and 1 of them has B, so that's 10 so far. That leaves us with 7 out of the 17 being left to have that C on them. Once you have labelled all of these, that is your diagram drawn. We have fulfilled this first part of the question. Now then, below that, if you've covered the Venn diagrams topic so far, especially for the A2, if you've watched that video, you'll have come across given that as an option, as a possibility for notation in terms of the Venn diagrams, in terms of how we can approach a probability question. Basically, if you need a reminder, if you haven't covered it yet, if we now have a statement that's given that, we're no longer looking at the entire model. We're not looking at something out of one. The focus, our framework, is now just whatever thing is given. So in this case, given that both cards have the same letter, find the probability that the first card was a C. So, given that they both have the same letter, we're now only going to be looking at either this branch, or this branch. We're going to completely ignore all of the others now. It's going to be out of the combination of these three. And then, again, thinking back to the formulas we used with the Venn diagram, given that notation, so A given B was the same as the intersection between A and B divided by B. So in this case, we would be looking at what is the probability of first being C and second being C out of probability of the second being C. In this case, the probability of both of them being C, we'd find that by doing 7 over 17 times 7 over 17. And then in a rather large denominator at this point, we're now going to work out what the total probabilities for all three of these paths are added up. So that's going to be 9 out of 17 times 9 out of 17. Add the 1 out of 17 times by 1 out of 17. Add then that same 7 out of 17 times 7 out of 17. Putting this all into your calculator, you could, I suppose, do the denominator first as a single bit if you wanted to reduce space. Either way, once you get an answer for this, you should find that the probability is 49 out of 131. This is how we do a given that with a tree diagram. Just identify the branches that fit this description that is given, put that combined probability in the denominator, then the numerator is the probability of the specific path that we're then looking for. With that in mind, let's just see how you get along with one final other example. So on a farm, 19% of sheep are found to be pregnant. If a given sheep is thought to be pregnant, this assessment has a 1% chance of being incorrect. If a sheep is thought not to be pregnant, there is a 13% chance this assessment is incorrect. Draw this tree diagram, and then once you've done that, given that the assessment was correct, find the probability that the sheep was pregnant. So in this case, we've now got slightly different criteria that we're going to be working with. So the first tier, whatever, is going to be whether or not it's pregnant. And then the second tier is respectively going to be, was that assessment correct or incorrect? And in this case, we have different probabilities depending on which branch we took, because the different assessments have different chances of being incorrect depending on what the conclusion was in the first place. So just think what this tree diagram is going to look like, pause the video, draw it out for yourself, and again do the calculations at the bottom, then just press play again once you've done all that, when you're ready to compare. Okay. So for this final example, we're basically just back to like we had in the first question, just a binary outcome in the first case, so it's either pregnant or not pregnant, and then from each of these we have two further outcomes. So if we want, we just select pregnant and not pregnant, and then just because it's the order that's given here, I'm going to put the not correct on top, but of course you can put it whatever if you want, so long as the right numbers are going to go with the right notation, right? The right labeling. So in this case, the probability of being pregnant, that was your 19%. Again, these have to add up to a total, a whole. In this case, because it's percentage, we're going to want to add up to 100%. So we could have 81% here. To be clear, you could turn these into fractions or decimals if you wanted, if that was any easier for you. Again, so long as the value is correct. I'm going to stick with percentage though, because that's what the question gave us. Then, if the sheep was found to be pregnant, there was that 1% chance of being correct. So incorrect, that's now your 1%. So correct, therefore, is going to be 99%. And if the sheep was thought not to be pregnant, there was a 13% chance. So we'll have our 13% for that incorrect there, and your 87% for a correctness to be a counterpart for that. As for the given that statement, therefore, so we're given that the assessment was correct, therefore we're just going to be looking at one of these two branches here. Find the probability that the sheep was indeed pregnant, so that's specifically looking at this branch here. So we will have our 19% times by 99% over the combination of both the correct branches. So again, that 19% times by 99% add, and then that's 81% times by 87%. This altogether will give you an overall percentage probability of 21%.